NEC Section 450.3 Bone addresses the overcurrent protection requirements for transformers, specifically focusing on the secondary side. This section dictates that fuses or circuit breakers protecting secondary circuits must be rated or listed for operation at not more than 125% of the transformer's rated secondary current. This provision is in place to safeguard the transformer from overload and to ensure that the downstream circuits receive adequate protection. The key concept here is understanding how to calculate the maximum allowable overcurrent protection for the secondary side based on the transformer's rated secondary current. To determine this, you first need to identify the transformer secondary voltage in kilowatt-ampere or kilovolt-ampere rating. This information is typically found on the transformer's nameplate. Once you have these values, you can calculate the secondary current using the appropriate formula. For a single-phase transformer, the formula is secondary current equals kilowatt-ampere times 1000 divided by the secondary voltage. For a three-phase transformer, the formula is secondary current equals kilowatt-ampere times 1000 divided by the secondary voltage times the square root of 3, which is approximately 1.732. After calculating the secondary current, you multiply this value by 1.25, or 125%, to determine the maximum allowable rating for the overcurrent protection on the secondary side. For example, consider a single-phase transformer with a 10 kilowatt-ampere rating and a 240-volt secondary. The secondary current would be 10 kilowatt-ampere times 1000 divided by 240 volts, which equals approximately 41.67 amps. Multiplying this by 1.25 gives you 52.8 amps. Therefore, the maximum allowable rating for the overcurrent protection on the secondary side would be 52.8 amps. You would then select the next standard size fuse or circuit breaker that does not exceed this value. It's important to note that the NEC allows for the use of the next higher standard overcurrent device rating if the calculated value does not correspond to a standard size. However, this is subject to specific conditions outlined in the code, and it's crucial to consult the relevant sections of the NEC to ensure compliance. While the NEC does not explicitly limit the overcurrent protective devices to no more than 6 times the transformer's available secondary current, this practice is often employed as a reasonable approach to provide a balanced level of protection for both the transformer and the downstream circuits. This approach ensures that the overcurrent protection is sensitive enough to detect and respond to overloads and short circuits, while also preventing nuisance tripping caused by inrush currents or temporary overloads. In addition to the 125% rule, the NEC also addresses the protection of the transformer primary side. Section 450.3 provides guidelines for selecting the appropriate overcurrent protection for the primary side, taking into account factors such as the transformer's impedance and the available fault current. It's essential to coordinate the overcurrent protection on both the primary and secondary sides to ensure proper operation and prevent cascading failures. Another important consideration is the type of overcurrent protective device used. Fuses and circuit breakers have different characteristics and performance capabilities, and the selection should be based on the specific application and the requirements of the downstream circuits. Fuses, for example, offer excellent current limiting capabilities and can provide fast and reliable protection against short circuits. Circuit breakers, on the other hand, offer the convenience of being resettable and can be easily coordinated with other protective devices. When selecting overcurrent protective devices, it's crucial to consider their interrupting rating, which is the maximum fault current that the device can safely interrupt without failing. The interrupting rating must be greater than the available fault current at the point of installation. This ensures that the overcurrent protective device can effectively clear faults and prevent damage to equipment and personnel. Proper transformer protection also involves considering other factors such as voltage regulation, temperature rise, and insulation integrity. Transformers are designed to operate within specific voltage and temperature limits, and exceeding these limits can lead to premature failure or reduced performance. Regular inspections and maintenance can help identify potential problems and ensure that the transformer is operating within its design parameters. This includes checking for signs of overheating, insulation degradation, and oil leaks. Additionally, it's important to verify that the transformer is properly ventilated and that the cooling system is functioning correctly. The NEC also addresses the installation requirements for transformers, including clearances, grounding, and ventilation. These requirements are designed to ensure the safe and reliable operation of transformers and to prevent hazards such as fire and electric shock. It's crucial to follow these requirements carefully when installing transformers to ensure compliance with the code and to protect personnel and property. In summary, NEC Section 450.3 provides comprehensive guidelines for protecting transformers from overloads and short circuits. The 125% rule for secondary overcurrent protection is a fundamental requirement that must be followed to ensure the safe and reliable operation of transformers. In addition to this rule, it's important to consider other factors such as primary side protection, overcurrent device selection, interrupting rating, and installation requirements. By adhering to these guidelines, you can effectively protect transformers and downstream circuits from damage and prevent potential hazards. Now let's consider some practical examples and scenarios to further illustrate the application of NEC Section 450.3. Imagine a commercial building with a three-phase transformer stepping down the voltage from 480 volts to 208/120 volts for general lighting and receptacle circuits. The transformer has a rating of 75 kVA. To determine the maximum allowable overcurrent protection for the secondary side, we first need to calculate the secondary current. Using the formula for three-phase transformers, the secondary current is equal to 75 kVA times 1000 divided by 208 volts times 1.732, which equals approximately 208.1 amps. Multiplying this by 1.25 gives you 260.13 amps. Therefore, the maximum allowable rating for the overcurrent protection on the secondary side would be 260.13 amps. In this case, you could use a 250 amp circuit breaker or a set of fuses rated at 250 amps, as this is the next standard size that does not exceed the calculated value. It's important to note that the overcurrent protection should be located as close as practical to the transformer secondary terminals to provide the best possible protection. This minimizes the length of unprotected conductor and reduces the risk of damage from short circuits or overloads. Another scenario might involve a small industrial facility with a single-phase transformer supplying power to a critical piece of equipment. The transformer has a rating of 25 kVA and a secondary voltage of 480 volts. Using the formula for single-phase transformers, the secondary current is equal to 25 kVA times 1000 divided by 480 volts, which equals approximately 52.8 amps. Multiplying this by 1.25 gives you 65.1 amps. Therefore, the maximum allowable rating for the overcurrent protection on the secondary side would be 65.1 amps. In this case, you could use a 60 amp circuit breaker or a set of fuses rated at 60 amps, as this is the next standard size that does not exceed the calculated value. In this scenario, it's particularly important to select an overcurrent protective device with an appropriate interrupting rating, as the available fault current at the equipment location may be relatively high. It's also crucial to ensure that the equipment is properly grounded to minimize the risk of electric shock. Now let's consider some of the exceptions and special cases that may apply to transformer overcurrent protection. The NEC recognizes that in certain situations, the standard 125% rule may not be appropriate, and it provides alternative methods for protecting transformers. For example, if the transformer is equipped with internal thermal protection, the overcurrent protection may be sized based on the transformer's thermal characteristics. This allows for a higher overcurrent protection rating, as the internal thermal protection will trip the circuit if the transformer overheats. Another exception applies to transformers that are part of a listed assembly, such as a motor control center or a power distribution unit. In these cases, the overcurrent protection may be sized based on the listing requirements for the assembly. It's important to consult the listing information to determine the appropriate overcurrent protection for the transformer. The NEC also addresses the protection of control transformers, which are typically used to supply power to control circuits in industrial equipment. Control transformers often have relatively low kilowatt-ampere ratings, and the overcurrent protection requirements may be different from those for larger power transformers. In general, control transformers should be protected by fuses or circuit breakers that are sized to protect the transformer from overloads and short circuits. The size of the overcurrent protection should be based on the transformer's nameplate rating and the recommendations of the manufacturer. In addition to the NEC requirements, it's important to follow any applicable local codes and regulations when installing and protecting transformers. Local codes may have additional requirements or restrictions that must be followed to ensure compliance. It's also a good practice to consult with a qualified electrical engineer or contractor to ensure that the transformer is properly protected and installed. They can provide expert guidance on selecting the appropriate overcurrent protection and ensuring that the installation meets all applicable codes and standards. Finally, it's important to remember that transformer protection is an ongoing process. Regular inspections and maintenance are essential to ensure that the transformer is operating properly and that the overcurrent protection is functioning correctly. This includes checking the overcurrent protective devices to ensure that they are in good condition and that they have not been damaged or tampered with. It also includes testing the overcurrent protective devices to verify that they will trip properly under overload or short circuit conditions. By following these best practices, you can help ensure the safe and reliable operation of transformers and protect personnel and property from potential hazards. The application of NEC Section 450.3 requires a thorough understanding of transformer characteristics, overcurrent protection principles, and applicable codes and standards. By following the guidelines and recommendations outlined in this section, you can effectively protect transformers from overloads and short circuits and ensure the safe and reliable operation of electrical systems. Remember to always consult the latest edition of the NEC and any applicable local codes before installing or modifying transformer protection systems. Let's dive deeper into the practical considerations for selecting and coordinating overcurrent protective devices for transformers. The choice between fuses and circuit breakers depends on several factors, including the application, the available fault current, and the desired level of coordination. Fuses offer several advantages, including their high interrupting rating, excellent current limiting capabilities, and relatively low cost. They are particularly well suited for applications where high fault currents are expected, as they can quickly and reliably interrupt the circuit. Fuses also provide excellent protection against short circuits, as they can clear faults very quickly, minimizing the amount of energy that is released into the system. However, fuses have some limitations. Once a fuse has blown, it must be replaced, which can be inconvenient. Fuses also require careful coordination to ensure that they will trip properly under overload or short circuit conditions. Circuit breakers, on the other hand, offer the convenience of being resettable. After a circuit breaker has tripped, it can be reset, which can save time and money. Circuit breakers also provide good protection against overloads and short circuits, although their interrupting rating may be lower than that of fuses. Circuit breakers require careful coordination to ensure that they will trip properly under overload or short circuit conditions. When selecting circuit breakers for transformer protection, it's important to consider their trip characteristics. Circuit breakers are available with different trip curves, which define the relationship between the current and the tripping time. The trip curve should be selected to provide adequate protection for the transformer while also preventing nuisance tripping. For example, a circuit breaker with a slow trip curve may be used to protect a transformer that is subject to frequent inrush currents, while a circuit breaker with a fast trip curve may be used to protect a transformer that is supplying a critical load. Coordination is a critical aspect of transformer protection. Coordination involves selecting and setting the overcurrent protective devices so that they will trip selectively under overload or short circuit conditions. This means that the overcurrent protective device closest to the fault should trip first, while the upstream overcurrent protective devices should remain closed. Selective coordination minimizes the extent of the outage and ensures that only the affected portion of the system is de-energized. To achieve selective coordination, it's necessary to carefully analyze the system and select overcurrent protective devices with appropriate time current characteristics. Time current curves show the tripping time of an overcurrent protective device as a function of the current. By comparing the time current curves of different overcurrent protective devices, it's possible to determine whether they will coordinate properly. In general, the upstream overcurrent protective device should have a time current curve that is above and to the right of the downstream overcurrent protective device. This ensures that the downstream overcurrent protective device will trip first under overload or short circuit conditions. Another important aspect of transformer protection is grounding. Grounding provides a path for fault current to flow back to the source, which helps to clear faults quickly and safely. Grounding also helps to reduce the risk of electric shock by providing a low impedance path for current to flow to ground in the event of a fault. Transformers should be grounded in accordance with the requirements of the NEC. The NEC specifies different grounding methods for different types of transformers depending on the voltage, the system configuration, and the application. In general, the transformer secondary winding should be grounded to provide a low impedance path for fault current to flow back to the source. The grounding conductor should be sized in accordance with the requirements of the NEC and should be securely connected to the transformer and to the grounding electrode system. In addition to grounding the transformer secondary winding, it's also important to ground the transformer enclosure. The enclosure should be grounded to provide a low impedance path for current to flow to ground in the event of a fault. The grounding conductor for the enclosure should be sized in accordance with the requirements of the NEC and should be securely connected to the enclosure and to the grounding electrode system. Regular inspections and maintenance are essential for ensuring the continued reliability of transformer protection systems. Inspections should be performed on a regular basis to check for signs of damage, wear, or corrosion. The overcurrent protective devices should be inspected to ensure that they are in good condition and that they have not been tampered with. The grounding connections should be inspected to ensure that they are tight and secure. Maintenance should be performed as needed to repair any damage, replace worn parts, and clean the equipment. The overcurrent protective devices should be tested periodically to verify that they will trip properly under overload or short circuit conditions. The grounding system should be tested to verify that it is providing a low impedance path for fault current to flow back to the source. By performing regular inspections and maintenance, it's possible to identify and correct potential problems before they can lead to equipment failure or safety hazards. Proper transformer protection is essential for ensuring the safe and reliable operation of electrical systems. By following the guidelines and recommendations outlined in the NEC and by implementing a comprehensive inspection and maintenance program, it's possible to protect transformers from overloads and short circuits and to minimize the risk of equipment failure and safety hazards.